Most of you are aware that the Earth is a magnet. Most of you are probably not aware of just how important that is. To start explaining the Earth's magnetic field to you, I will start with a PhET simulation. This simulation shows us a bar magnet. It has one side labeled north in red and the other side labeled south in white. Remember, the poles just tell us where most of the field lines come in and out of the magnet. The simulation is cool because we can see the domains inside the magnet. Notice how there are not just reds on one side and whites on the other side. Each domain has its own small north and south side. All of the microscopic domain north poles line up to form the macroscopic north pole. Some real magnets actually come with the N and S labels branded onto them. That's actually a little silly because you could just use a strong external magnetic field to flip the domains and have the actual south side be on the side that's advertised as the north side. Anyway, I can use the PhET simulation to place a compass in this environment. Notice that the compass arrows use the same red and white color convention. That's because the compass is a magnet, with a little north and a little south side. The compass needle has very small mass, and it's on a nearly frictionless bearing that allows it to spin freely. Notice that the north side of the compass is attracted to the south side of the bar magnet. It should come as no surprise that the south side of the compass is attracted to the north side of the magnet. This is nothing new. Opposites attract. I can turn on the blanket data in the simulation. You can see that it displays tiny compasses in a regular lattice pattern. The red sides of the arrows are pointing downhill. Bright compasses are showing steep slopes. Dim compasses are indicating shallow slopes. See how the macroscopic compass tool is really telling me the direction of the slope of the magnetic blanket? Compasses only show the direction of the slope, but do not give magnitude. Now that we understand how the simulation works, let's bring in a different magnet, the Earth. Watch what happens when I bring the compass to this side of the Earth. Is that what you expected? Let's check the other side. That's probably not what you expected either, but at least it's consistent. What's going on here? The north side of the compass points north, and the south side of the compass points south. I thought we just said that opposites attract. Is the compass broken? Why would you simulate a broken compass? Here's what's really going on. The Earth spins on its axis, causing us to have a day and night cycle. The places where we imagine the axis pokes through the skin of the Earth are called the geographic poles. This one is called north, this one is called south. Our compass is not attracted to geographic poles, it's attracted to magnetic poles. The place that we call geographic north is actually magnetic south. The place that we call geographic south is actually magnetic north. That's pretty weird, and it gets worse. The Earth has been spinning on its axis for 4 billion years. It has slowed down a lot in that amount of time, but the axis itself has been constant. Geographic north has been in the same place since the Earth became the Earth. The magnetic poles are not permanent. In the last 200 years, the magnetic south pole has been moving steadily away from Canada and towards Russia. This graph shows that in 1900, the magnetic south pole was in northern Canada. Today, it's actually pretty close to the geographic north pole. The poles are currently moving at a pace of about 34 miles per year. Why are they moving? The Earth is a magnet because it contains a lot of iron and nickel inside of it. However, unlike a bar magnet that is solid, the inside of the Earth is molten. The middle of the Earth is very hot and the outside is very cool. This is important. When you boil water on the stove, you get convection currents in the water. Hot water rises to the top of the pot and cooler water goes down to the bottom. As long as the stove is on, the convection currents will keep happening. So it is with the Earth. The molten material convects, changing the distribution of the magnetic material over time. This shows up as pole migration. Scientists have been graphing this pole migration since 1830. The poles have moved 1,400 miles since then. There is no reason to think that the pole migration started in 1830. It has probably been going on for 4 billion years. How can we find evidence for this? Here's another picture of the Earth. This is the Atlantic Ocean. Do you know what this is? It's the Mid-Atlantic Ridge. It's a huge fault line that separates major tectonic plates in the Earth's crust. It's basically a 10,000-mile-long volcano. The Atlantic Ocean is only 180 million years old. Before that point, the Americas were actually touching Europe and Africa. As magma squirts up out of the ridge, it cools and forms new rock, pushing older rock out of the way. The newest rock is right next to the ridge. The oldest rock is touching the coasts of the continents. In the 1980s, someone had an idea. They decided they could use a VCR reader head to read the floor of the Atlantic Ocean and study pole migration. Here's a simplified explanation of the experiment. You get in a boat with your VCR, and you put the reader head on a long pole that goes down to the rock layer. The lava coming out of the ridge contains iron. As the lava cools into rock, the domains in the iron line themselves up with the Earth's magnetic field. New rock that formed today would contain iron that's pointed this way. If, in the past, the magnetic pole was over here, then the magnetic domains of rock that formed at that time would be pointed this way. So let's imagine that our VCR boat crosses the ocean reading the rocks. Here's what they see. Do you get what I'm trying to draw? Notice that I'm drawing mirror image domains on either side of the ridge. That's because lava that comes out goes to each side as it forms new rock. These rocks are the same age and have the same domain alignment. These rocks are the same age and have the same domain alignment. In my drawing, I'm suggesting that the magnetic poles have flipped around twice. But it's actually way more than that. Just in the last 80 million years, the poles have reversed 183 times. On average, it happens every 300,000 years. To us, that's a long time, but to the Earth, it's really not a long time at all. So now that we know why the Earth is a magnet, let's talk about why that's important. As you know, we get all of our light from the sun. But the sun does not just send us light. The sun also sends out a ton of high-energy protons. This is called the solar wind. These protons are dangerous. When they hit an atom, they can destroy it. If they happen to hit atoms in the cells in your body, they can do one of three things. They can kill the cell, which is actually the best case scenario. They can mutate the cell and give you cancer. Or they can mutate a sex cell in a way that gets passed on to your offspring. A little of this is a good thing. That's the process that drives evolution. A lot of it is a bad thing. Luckily, we have our magnetic field to help us out. In a previous video, we talked about magnetic steering. When a charged particle enters a magnetic field, the magnetic force is centripetal and it turns the particle around and sends it away. We usually think of the Earth's magnetic field as a surface feature that just helps us navigate, but the magnetic blanket of the Earth is actually huge. At this scale, the Earth's atmosphere is literally just the width of this line that defines the circumference of the globe. You can see that most of the Earth's magnetic field is way outside the atmosphere. The solar wind is blocked from getting to the Earth by our magnetic field, almost everywhere. There are two places where the magnetic field dips down into the atmosphere, at the poles. At these locations, the solar protons can collide with the nitrogen and oxygen in our atmosphere. When that happens, we get the auroras. They happen 24 hours a day, but they are only visible at night. Planets without magnetic fields cannot support life. The solar protons would prevent any life from forming. Not all planets have magnetism. The Moon doesn't. Mars used to, but it is gone now. When scientists look for planets that could support life, they look for three things: a good temperature, abundant water, and magnetism. As important as the Earth's magnetic field is, it's also important to realize that it's not very strong. Here's an interesting list of the strengths of different magnets. Okay, so the Earth is 50 microteslas, 50 millionths of 1 Tesla. A fridge magnet is about 5 milliteslas, so it's about 10,000 times stronger than the field of the Earth. A junkyard magnet, like the ones they use to pick up cars, are 1 Tesla. The magnet in a medical MRI machine that they have at the hospital is 3 Teslas. The biggest MRI machines in the world used in research labs are 10 Teslas. Here's another interesting list. In 1992, the biggest man-made magnetic field was 34 Teslas. In 2012, it was 100 Teslas. And in 2018, it was 1,200 Teslas. As you can see, we're getting better at making magnets.